Hello students, so we are continuing electromagnetic induction today. In the previous session we got an introduction about electromagnetic induction. So what is electromagnetic induction? A current carrying coil, when it acts as a magnet, it will induce an EMF or current in another coil if we move it towards and away from it. That is, whenever there is a change in magnetic field or in the presence of magnetic field, if there is an increase or decrease of magnetic field, or if there is any change in area of the loop, or if there is any change in the magnetic field area or in the orientation of the loop, that is orientation of the area. That is, we saw that the magnitude of induced EMF is d phi by dt, okay, and phi is equal to b dot a or ba cos theta. Okay, so we have seen three experiments, like if this is a loop which is connected to a galvanometer, if we bring a bar magnet, okay, towards it, there is a deflection. If it is moving away from it, there is a deflection in the opposite direction. If we change the pole and if we are bringing south pole, then the deflection is in the opposite direction. Now instead of bar magnet, if we keep a current carrying coil, and if this thing, if we bring it towards this coil or away from this coil, we were observing the same phenomenon. Other than that, if the coil doesn't have any movement, but if this is a switch, if we on the switch, off the switch continuously, on off, still we got the deflection here. So all these deflections are because of what? This was the studies Faraday and his team, they were undergoing, or they were trying to understand. So we came to know that the electric field induced in the coil, okay, is nothing but change in the flux due to the change in flux, okay, due to the change in flux. So what is magnetic flux? Magnetic flux is the flux passing through an area, that is magnetic field. So not flux is nothing but magnetic field lines passing through an area. So magnetic field lines passing through an area is nothing but that magnetic field into area. Since magnetic field is also a vector, area is also a vector, we cannot do ordinary multiplication. So what we did, we put dot product. Why dot product? Because this magnetic flux is not a vector, this is a scalar. So already we have studied in vector basics, okay, if this one or the result is scalar, the multiplication between two vectors will be dot product. If the result is vector, then multiplication will be what? Cross product. We have already studied this. So phi is equal to b dot a or ba cos theta. Now if this EMF, magnitude of induced EMF, if we do d by dt of ba cos theta, see, if we change the magnetic field, electric EMF will be induced. That is what we were doing here. If this magnet coming near to it, magnetic field will be increasing, that will produce EMF. If it is moving away, then magnetic field will decrease, that is also a change, right? So that is one reason for induced EMF. Another is area. If we increase or decrease the area, practically speaking, even though it is difficult, but conceptually, if we decrease the area, increase the area of the coil kept in the magnetic field, what will happen? if magnetic field is going inside, if we keep a coil here, okay, if we could practically, if we could increase the area of the coil, then what will happen? EMF will be induced. EMF will be induced. Another thing is, what is this theta? What is this theta? Suppose this magnetic field is going inside, and if we keep a coil like this, so this is area vector. What is the direction of area vector, students? What is the direction of area vector? If my palm, if this is an area, the direction of area vector of my palm will be normal to it. Okay, either this can be in this side or that side, both are possible. Okay, so if this is magnetic field and if we keep a loop, then either the area will be normally parallel to the loop, or if it is coming out, then it is exactly at 180 degree. So this theta is the angle between magnetic field and area, magnetic field and area vector. Okay, so but just by changing the orientation, just like if this magnetic field is going from this towards you, this is north pole and you are sitting at the end of south pole, magnetic field is going like this. Now suppose if we keep a current carrying loop like this, now magnetic field is in this direction, area vector is in this direction. Okay, both are parallel, angle is 0, so phi is VA. Now if we change the loop, if we rotate the loop like this, now area vector is 90 degree to the magnetic field vector. This is now 0. Now this, what is happening here? This is changing, cos theta is changing here. So this change also can bring EMF. Now this is rotating. So when it is rotating like this, what is happening? Continuously changing the magnetic flux. Continuously changing the magnetic flux, which will bring EMF. This is the concept of generator. Generator rotating, no, coil will be rotating inside the generator. Okay, so generation of electricity, all based on this concept. Okay, we will study that later. Now the thing which we need to understand is the rate of change in flux is what is EMF. Okay, d by dt of phi. Okay, d by dt of phi. Okay, this is instantaneous. Even we can write like this also. EMF is equal to phi 2 minus phi 1 divided by the time duration. Okay, I am putting here only magnitude. I am putting mod there just because one negative sign will come there, that we will study. Okay, negative sign will come there. Actually, without mod, if we write, it is exactly, it is like this. E is equal to minus d phi by dt. E is equal to minus d phi by dt. If there are n number of turns in the coil, we can write this also. If there are n number of turns in the coil, we can write n also. Okay, so this is the concept we have studied in the last session. Now we will do problems on this today. Okay, let us see. A square loop of side 10 centimeter, a square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in east-west plane. Okay, a uniform magnetic field of 0.1 Tesla is set up across the plane in northeast direction. The magnetic field is decreased to 0 in root 2 seconds. Okay, at a steady state. Determine the magnitude of induced EMF and current during this time interval. Okay, during this time interval, and options are also given, like 0.5 millivolt, 1 milliampere, 1 millivolt, 0.5 milliampere. Likewise, for options of induced EMF and induced current, both are given. Okay, now let us see. See, a square loop of side 10 centimeter. Okay, and resistance 0.5 ohm is placed vertically in east-west plane. Okay, so north, south, east, west. Okay, so east-west plane, it is kept in east-west plane. In which direction? kept vertically in east-west plane. Okay, kept vertically in east-west plane. A uniform magnetic field of 0.1 Tesla is set up across the plane in northeast direction. So northeast direction is this. Okay, northeast direction is this. Right. So magnetic field direction is like this. Suppose if we draw a line like this, north east plane means this will be 45 degree. So this is the direction of magnetic field, that is in northeast plane. Now they have kept vertically a loop, they have kept a loop vertically in east-west plane. Okay, in east-west plane they have kept a loop in vertical direction in east-west plane, and magnetic field is going in this direction. So this is the setup that what we have here. Okay, right. Now what extra data is given? The magnetic field is decreased to 0 in √2 seconds. Determine the induced EMF. Right. So induced EMF is equal to phi2 minus phi1 divided by the time duration. Okay, so what is phi1? Phi1 is B dot A. Okay, so magnetic field is given as 0.1, and what is area? Side is given. Side is given as 10 centimeter. Side is given as 10 centimeter. So this is a square loop, so L square we can say 10 into 10 raised to minus 2 into square. Okay, so this is what is the area. So 10 into 10 raised to minus 2 whole square, and B dot A, so cos 45. This is the angle between them. Okay, cos 45. So this is what is phi1. Now what about phi2? They have, it is decreased to, magnetic field is decreased to 0. Okay, magnetic field is decreased to 0. So B dot A, if we take this, magnetic field is decreased to 0. So whatever happens, this will become 0. Correct. Right. Now we will find the EMF. So EMF is equal to phi2 minus phi1. So phi2 is this one, 0.1 into 100 into 10 raised to minus 4 into what is cos 45? 1 by √2 divide by this time is given, like a magnetic field is decreased to 0 in √2 seconds. So we will put √2 here. √2 here. Okay, please look at the solution. Is that okay? Everything is fine? Are you able to understand? Okay, clear? Right. So this is also what, 10 raised to minus 4. If we consider this is just like 100 into 10 raised to minus 5 divided by 2. So we can write this as 50 into 10 raised to minus 5, 50 into 10 raised to minus 5. Okay, this is the EMF. So from the options, which can be correct? 0.51. Okay, so 0.5 millivolt is given as option A, 0.5 millivolt. So 10 raised to minus 3 if we take, this is going to be 0.5. Okay, if we take 15 to 10 raised to minus 5, so this is correct. Okay, 0.5 millivolt is correct. So this is one answer. Okay, so we can directly mark option A because none of other options are giving this answer. No need to find the current. Okay, according exam point of view, when you are attending exam, one option is correct, directly you can go. But here for learning purpose we will have to take that also. So current is equal to what? E by R. 0.5 millivolt is the EMF. Now resistance is given as 0.5. So we will be getting 1 milliampere. Clear? Understood? Clear? Right? So I'll explain once again. First data is a coil of 10 centimeter side, okay, a square coil. So okay, for the time being I am considering this phone as a square coil. Okay, so 10 centimeter one side. This is kept vertically in east-west plane. So always when we get north, south, east, west, how we will mark north, south, east, west. So this is what is east-west plane. So this is kept vertically in east-west plane. Vertically means any direction. Okay, only that much they have said. Okay, so east-west plane they have kept vertically. Okay, so this is what is east-west plane. Now they have given like a magnetic field is given in northeast direction. Northeast direction means this direction. Okay, this is north, this is east. So northeast direction. So area vector is this direction, or area vector can be taken in this direction also. But take 0, that is important, that is easy. Even if you take area vector as this, okay, answer you will be getting same answer you will be getting, but we will have to do some more measurement. Directly we cannot take, we will have to consider which angle. This 45 degree, this way we will have to take. 90 degree plus 45 degree we will have to take. So instead of that, take it as 0 degree. So take it area vector like this. This is the direction of magnetic field. That is the first position. So phi 1 we can calculate just by doing B dot A, which I have done here. Okay. Phi 2 magnetic field is directly decreased to 0 in root 2 seconds. So time duration is root 2 seconds. Magnetic field is 0. So phi 2 is 0. Now EMF is what? Phi 2 minus phi 1. So 0 minus this one. Okay. Divide by T. Okay. T is given as root 2 seconds. Okay. Phi 2 minus phi 1 means 0 minus, I will have to put here now, so minus will come. Okay, but in the options negative is not given. Okay, why? What is the direction of current, induced current? All these things will exclusively dealt by a law called the Lenz's law. That is another topic. Now we don't worry about the negative sign and all. Directly we will calculate this. Okay, clear? So EMF we found, then current also we got. Clear? So we'll move to next question. Second question. A circular coil of radius 10 centimeter and 500 turns and resistance 2 ohm is placed with its plane perpendicular to horizontal component of Earth's magnetic field. It is rotated about its vertical diameter through 180 degree in 0.25 seconds. Estimates the magnitudes of EMF and induced current in the coil. Magnetic field is given. Horizontal magnetic field is given in the question. Right. So again same thing we need to find. We have to find EMF. So what is EMF? Okay, d phi divided by dt. D phi divided by dt. Okay, so here number of turns are given. Okay, so this is a coil with 500 turns, so we will put n here. Okay, the actual formula is like if it is mod, then we can write like this. If the actual formula, if we consider E is equal to minus n d phi divided by dt. Okay, so this time we shall consider negative sign also, and let us see what difference it is going to make. So right, so first data is it is kept in a plane perpendicular to horizontal magnetic field. Suppose horizontal magnetic field is this. Okay, then it is given, this data is given as 3.0 into 10 raised to minus 5 Tesla. Okay, this is horizontal magnetic field. How the loop is kept? The loop is kept with its plane perpendicular to horizontal component of Earth's magnetic field. That is, if this is the direction of magnetic field, plane is kept perpendicular to it. So this is plane of the loop, this is the magnetic field direction. So this is what is kept perpendicular means. Okay, otherwise plane will be kept parallel to it, we can say. Okay, so this is how, okay, if it is a circular loop, then we can take like this is how it is kept, and this is the area vector. Clear? That is the area vector. So this is the first data. Now what happens is, if it is kept like this, it is just changed, rotated in vertical direction. See, it is rotated about its vertical diameter through 180 degree in 0.25 seconds. So second data is like, so this is can be taken as phi1. If again this is magnetic field, this time it is rotated, okay, it is rotated vertically in the opposite direction. Now the area vector is like this. Okay, so from here we will have to find phi2. So what is phi1? Phi1 is again B dot A. B is given as 3 into 10 raised to minus 5 into A is pi r square, it is circular loop. So pi into what is radius, 10 centimeter, 10 into 10 raised to minus 2 the whole square. So B dot A. Now what is the angle? The angle is cos 0, because area vector, magnetic field, both are in the same direction, right? So this is phi1. What about phi2? Phi2 can be written like again same magnetic field, 3 into 10 raised to minus 5 into area is also what, same, pi into 10 raised to minus 2 the whole square into what, cos. This was in this position, now it is rotated like this. So cos 180 degree. Magnetic field direction is this, area direction is this. So cos 180 degree. Okay, so what we are getting, we will be getting, this is again 0, but this here negative will come. So 3 into 10 raised to minus 5 into pi into 10 raised to minus 2 the whole square. So phi1 and this is phi2, right? So EMF is equal to what, negative of, this time we will consider this negative sign, okay, negative sign, negative of 500 turns are there, that also will put, into d phi by dt. So this is just like a minus n into phi2 minus phi1 divided by t. Okay, so phi2 is what, minus 3 into 10 raised to minus 5 into pi into 10 raised to minus 2 the whole square. I'm sorry. Okay, 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 fine. So here pi into 10, okay, pi into 10 into 10 raised to minus 2 the whole square. Okay, so this is phi2, okay, phi2 minus phi1, okay, phi1. So phi1 is 3 into 10 raised to minus 5 into pi into 10 into 10 raised to minus 2 the whole square. So phi 2 contains a negative sign, minus phi 1 doesn't have a negative sign, so minus phi 2 is coming here, minus of phi 1. Okay, so what we will have to do, we will have to add these both because their signs are same. So we will solve like that. So E is equal to minus 500 into 2 into, so that will become cancel. Okay, negative will come here. 2 into 3 into 10 raised to minus 5 into pi into 100 into 10 raised to minus 4. Okay, so everything is there. Now just simplifying this, we will be getting the EMF value. Okay, so 3 pi into 10 raised to minus, so if we do this, this will become 1000. Okay, so this is 10 raised to 3. Okay, now this is just 3 into pi into, here this is 10, this will become 10 raised to minus 2, this will become 10 raised to minus 7. Okay, so we will be getting 3 pi into 10 raised to minus 4. Correct? So what about the option 3 pi into 10 raised to minus 4? Okay, so one data we have forgotten here, that is nothing but E is equal to d phi by dt, right? So that we didn't put. So 0.2, how 0.25 seconds, so that also we need to put here. So this divide by 0.25 seconds, so 0.25. So if we put 0.25, this will become 1 by 4. So finally the answer will become, this will go here, 12 pi into 10 raised to minus 4 volt. This is the induced EMF. Okay, now what we need to find, we need to find the induced current also, because resistance is given. So induced current is going to be 12 pi into, that is E by R. E by R. So 12 pi into 10 raised to minus 4 divided by R is 2 ohm. So this is going to be 6 pi into 10 raised to minus 4 ampere. Okay, 6 pi into 10 raised to minus 4 ampere. Okay, so understood? Note down the solution. Note down the solution. Noted? Done? Right. Now I told you we will put a negative sign here and we will see the answer. So as we discussed, I put a negative sign here. E is equal to minus, we put here according to this formula. Now suppose if we don't put this, then what difference will happen here? See, this is B dot A cos 0. Okay, this is phi 2. So here negative will come just because of cos 180. So that we will have to put. This cos 180 negative we will have to put. Okay, matter of calculation. So minus we put here. Here part of formula phi 2 minus phi 1. So here also this negative also will have to put here. Negative. Finally what will happen? This will become minus. So if we remove this negative, anyway this part simplification will not have any change. So that will be there. Again what will happen? Since this negative we haven't considered, when we take out this negative will not be cancelled in the final result. So in the final result what will happen? One negative will come. In the current also one negative will come. But in these kind of questions, look at the option, they have given only magnitude. So they are not bothered about negative sign in these type of questions. They will bother about that real direction only in Lenz's law. So here, even though if you neglect this negative sign, nothing will happen. So when you get this question, for safer side, when you get these kind of questions, first you look at the option. In the option, negative is not at all there, then you need not put this negative in the answer. But here, based on the angle, whatever be the sign, that must be accurate. Cos 180, here if you miss one negative, the answer will go wrong. Okay, clear? Understood? I hope you understood this question. We'll go to third one. So third question is a loop of wire. A loop of wire is placed in magnetic field B is equal to 0.3 J Tesla. 0.3 J. Right? 0.3 J or 0.3 J Tesla. Then find the flux through the loop if area vector is. So they have given this in vector form. It is simple question. Nothing is there. Magnetic field B is given as 0.3 J Tesla and area vector is given as 2I plus 5J minus 3K. Okay, meter square. What they are asking? They are asking flux, magnetic flux through the loop. Magnetic flux through the loop. So very simple question. Phi is equal to B dot A. We know, we are very comfortable in vector multiplication, right? So 0.3 J, okay, dot what? Area vector is 2I plus 5J minus 3K. So 0.3 into 5J, what will come? So this is just like 0I plus 0.3J plus 0K. What? This magnetic field is like dot 2I plus 5J minus 3K. We know in dot product only respective terms we will multiply. Okay, so 0I, 2I, will, if you multiply that will become 0. 0.3 into 5 is what? 1.5 J plus this one if you multiply that will become K. So phi is, I'm sorry, J will not come, I'm sorry, really sorry. There won't be any direction. So 0.3 into 5 is 1.5. So 1.5 Weber. So this is the answer for this question. Okay, only thing is just you should know the formula and you must know how to do the dot product. Okay, clear? We'll go to next question, fourth one. At a given plane, horizontal and vertical component of Earth's magnetic field, okay, BH and BV are along X and Y axis respectively, okay, as shown in the figure. What is the total flux of Earth's magnetic field associated with an area S, if area S is? First question is A, that is XY plane. Okay, we will deal one by one. That is actually with a common data, that is 3 questions. There are 3 questions. Only changes area is in XY plane, one area is in YZ plane, another area is in ZX plane. Okay, right. So what is the figure given? Figure is also given. Okay, figure is given like this: X, Y, Z. Okay, so they have given like BV is in this direction and BH is in this direction. Okay, now area is in XY plane. Area is given, first area is given in XY plane. So XY plane is this, so this area is like this, and area is in XY plane means there its direction is given as in Z direction. See, if this is X, this is Y, towards you, line towards you is Z, means if I keep an area, what is the direction of this area vector? Okay, area vector is towards you. Okay, area vector is normal to the plane of the area. Okay, so this is the figure. Now what they are asking is, what is the flux, magnetic flux? So phi is equal to, we know, B dot A. Phi is equal to B dot A. Right. So what is B? Look at the option BHS, BVS, 0, BH, SZ. Not numerical values. We will have to write magnetic field in terms of vector. Okay. See, B is equal to BH. In which direction? Positive X direction. So I can write BHI. No worries. What about BV? This is minus BV into J, because this is in negative Y direction. That is the reason I have written this as minus J. So this is what is magnetic field. Now what about area vector? Area vector is given as S. Okay, so S vector is nothing but its magnitude is what? S. So S into, in which direction? In Z direction. So we'll write it as K. So we got magnetic field and S. Okay, and area vector. So phi is equal to B dot A. So BHI minus BVJ dot SK. Right. So in the previous question I have shown you, okay, when you do dot product, just put 0I, wherever components are not written, just put it as 0. This is like a BHI minus BVJ plus 0K. Okay, this is the complete form. Here this is just like a 0I plus 0J plus SK. So when you do dot product, here this will give 0. If you multiply this, that will give 0. This will also give 0. So magnetic flux will be 0. Magnetic flux will be 0. Option C. Option C. Clear? Clear? Right? So nothing. This figure is given. So from the figure, I can understand that what is the direction of vertical magnetic field, what is the direction of horizontal magnetic field. So the net magnetic field is nothing but BHI minus BVJ. Area vector is given, its direction is given in the Z direction, so SK. Then we are doing dot product, nothing else. Okay, so next question, just look at the figure, pause the screen, do yourself and verify the answer. Okay. Okay, pause the screen. So B, question B. So question B is in which plane? Question B in YZ plane. YZ plane. YZ plane. So here they have given the figure in this way. Okay. YZ plane. YZ plane direction is given like this. So now this is in this plane. Okay. Is there any change in magnetic field? Magnetic field same, BHI minus BVJ, right? What about the area vector? Area vector is in which direction? Instead of SK, what should I put? Tell me, what should I put here instead of SK? Now what is the direction of area vector? Come on, this is going to be SI, correct? SI. Now I can replace this as SI. Now what will be the answer? Okay, I will be getting, remaining all the terms will become 0. Just the answer I am going to get is, I can multiply like this, BHS. This is the flux. Okay, magnetic flux is this. Option A. Clear? Understood? Okay. Shall we move to C? So for C they have given area is in XZ plane. Area is in XZ plane. So area is given like this time. Okay, just like this, direction is given like this. So what is the direction of area vector? Only area vector direction is changing here. Okay, so area vector, we can write it as Sj, correct? We can write the area vector as Sj. So when we do phi is equal to B dot A BHI minus BVJ dot Sj. So what we will be getting? Minus BVS. Correct? You got the same answer? Minus BVS. Option C. Option C. Clear? Shall we move to the next question? Fifth one. So fifth question, please read it. Fifth question. A coil of 100 turns, 5 centimeter square area is placed in an external magnetic field of 0.2 Tesla in such a way that, okay, so 100 turns, okay, fifth question, 100 turn area is equal to 5 centimeter square placed in an external magnetic field is given as 0.2 Tesla in such a way that it makes an angle 30 degree with the field direction. Okay, in a coil of 100 turns of 5 centimeter square area is placed in an external magnetic field in such a way that it makes an angle 30 degree with the magnetic field direction. Okay, calculate the magnetic flux through the coil, right? So suppose if this is the direction of magnetic field, okay, area is placed in an external magnetic field in such a way that it makes, okay, an angle 30 degree with the field direction. So it is just like if this is field direction, it is kept in such a way the coil is kept at an angle 30 degree. Okay, I'm sorry, not this one. Okay, like this, 30 degree with the field direction. Okay, this loop is kept in such a way that it is 30 degree with the field direction. Now can you tell me the answer? Pause the screen, look at the figure and give an answer. Okay, what answer you are getting? Okay, so see children, here if you take angle 30 degree, the answer will go wrong. Theta is equal to 30 degree will give wrong answer. Okay, if the loop is kept at an angle 30 degree means this is how it comes. Okay, the loop is kept at an angle 30 degree. Okay, so suppose if this is the loop, okay, if this is the magnetic field, then this is kept at an angle 30 degree means this is how. Okay, this is the direction of magnetic field. The loop is kept at an angle 30 degree means this is how. Okay, now suppose if we try to find flux B dot A or BA cos theta, this theta is actually, theta is angle between B and B magnetic field vector and area vector, not simply loop. It is the angle between magnetic field vector and area vector. So what is the direction of area vector? Just look at this carefully. The area vector is actually perpendicular to the field. that is perpendicular to the, not field, perpendicular to the area direction. That is, this will be, this red color I have shown, this will be the direction of it. See, when magnetic field is this blue color marker, magnetic field is this blue color marker, and my palm is the area, this angle is given as 30 degree. Actually what we need is, this is area vector, this is magnetic field, this angle is what we need. Okay, so suppose if this angle is now 90 degree, always area will be, vector will be 90 degree to the plane of the area. So if we take like that, then this angle is going to be 60 degree, 90 minus 30. So here phi is equal to, n is equal to 100 into magnetic field is 0.2 into area is 5 into 10 raised to minus 4 meter square, this is centimeter square, into cos 60. So 100, okay, cos 60 is 1 by 2. So if we cancel this, this will become divide by 10. Okay, so 100, 10 raised to minus 4, this will become 10 raised to minus 2, divide by 10, this 0.2 and cos 60, and into 5 here. So this is equal to 5 into 10 raised to minus 3 Webers. This is the answer. Okay, so while taking the angle between magnetic field and area vector, we have to be careful. Okay, that is the learning of this question. So next is question number 6. A square cube of side A is placed in a uniform magnetic field. Find the magnetic flux through the face A, B, C, D. Okay, so this is a square cube. Okay, square cube, right? So this is a square cube. So its sides are given like A, B, C, D. Okay, then E, F, G, H. Okay, so A, B, C, D, E, F, G, H. Now all the corners will have a letter. Now the magnetic field is passing in which direction? In this direction. Magnetic field is passing in this direction. So what they are asking is, what is the magnetic flux passing through the face A, B, C, D. Okay, so this is just like a square cube, just like this. Okay, just like this, a square cube is kept like this. Magnetic field is going in that direction. Okay, so here if we take the area vector of this phase, it is moving like this. Okay, so magnetic flux phi is equal to B dot A. So its side is given as A. Okay, so magnetic field B, that is given. Area is what? A square, and cos, what angle we can put? Directly we can put 0. So BA square. So this is the flux passing through ABCD. Suppose if we are asked to find the same question, considering this situation, if we are asked to find what is the flux passing through HGFE, that is this face. If the square cube is like this, that face. Okay, so here this is the area vector. This is the direction of area vector. So in this case, the angle will come as 180 degree. See, this question is taken in order to explain one concept. For an open area just like this also can be taken as direction, this also can be taken as direction, but in the starting of the problem, if we consider this as the direction of area, then we should stick on to that. For easy solving of the problems, we need not consider the opposite direction, we directly take 0. Why unnecessary hurdles? We do like that. But for a closed things like a cube or circle, they are all three-dimensional. So this is a cube. For that, area direction is always outerwards. Suppose if we consider this plane, its area vector is in this direction. If we consider this plane, area vector will be this direction. This face, area vector will be towards us. This plane, area vector will be in that direction. Clear? Understand? So this face HDE, HGEF, this is actually facing in this direction. Suppose if this is a box, here this face, this is what is HGFE. Okay, so that is the reason I have taken 180 degree as the direction. So BA square cos 180 degree, we will be getting BA square as the answer. So there is no doubt in this. If the magnetic field is given like this, suppose if they are asking the magnetic flux passing through this phase, definitely this is going to be the answer, because we don't have any other option except taking the area vector in this direction. Okay, right. Suppose if they ask what is the magnetic flux passing through HDCG or AEFB. So here magnetic field direction and area vector, they are at 90 degree. Theta is equal to what? 90 degree. So 0 will come. Cos 90 is 0. No other way. Okay, so if we take a cubical box like this and magnetic field is passing through that, then for each side what will be the magnetic flux if they ask? This is how we need to approach. What about this face and the other face? This is also 90 degree, this is also 90 degree. Okay, 90 degree. Which face? Phi of HEAD or here GCBF. So that also what? Theta is equal to 90 degree. This is going to be giving 0. Clear? Now hope you are clear about how to handle area vector, okay, and how to take flux. Clear, all of you? Clear? Understood? Shall we do the next question? Now take question number 7. Question number 7. The magnetic flux through a coil perpendicular to the plane. Okay, magnetic flux through a coil perpendicular to the plane is varying according to the relation phi is equal to 5t cube plus 4t square plus 2t minus 5. Calculate the induced current through the coil at, okay, I at t is equal to 2 seconds. Resistance is given as 5 ohm. Already in motion in one dimension, when we have studied, okay, instantaneous velocity, instantaneous acceleration or instantaneous current, for all that what we do, we will just differentiate. Okay, so for finding E at t is equal to 2 seconds, first we will have to find E at t is equal to 2 seconds. So how to find? This is nothing but d phi by dt. d phi by dt. So just differentiating, we will be getting 15t square plus 8t plus 2. So this is what is e at t is equal to 2 seconds. Substituting 2 seconds here, we will be getting, so 15 into 4 plus 16 plus 2. So 15 to 4 60, 76, 78 volt. Okay, so 78 volt is the EMF. Now what we need to find? Current. Current is equal to E by R. So 78 divided by 5. This is the answer for this question. Clear? So remaining all phi 2 minus phi 1, all these things are average EMF. Phi 2 minus phi 1 by t is average EMF. Suppose if they ask at some particular instant of time, we will have to do d phi by dt. Clear? Note it down. Okay students, so these are the basic problems that we can do in finding magnetic flux and EMF, average EMF, instantaneous EMF, current average, instantaneous current, and how to deal with the area vectors, because in order to find flux, change in flux, area vector will come a lot here. Okay, so please try to do more number of questions of this type. Practice well, make your concepts very strong. Thank you students, goodbye, good luck.